Welcome to G Fun Facts Online. In the grand theater of geological time, glaciers are the master sculptors. These colossal rivers of ice, inching their way across continents and down mountain valleys, have carved some of the most dramatic landscapes on our planet. Think of the deep, majestic valleys of Yosemite, or the jagged, sky-piercing peaks of the Alps. The immense power of glacial erosion is etched into the very fabric of the Earth. But for centuries, understanding exactly how they do it and predicting how fast they do it has been a monumental challenge for scientists. How do you measure the forces at work under miles of grinding ice? Well, a powerful new tool is revolutionizing the field: machine learning. By harnessing the pattern-recognizing capabilities of artificial intelligence, researchers are finally beginning to predict the erosive power of glaciers with unprecedented accuracy, unlocking vital secrets about our planet's past, present, and future. So today, we're talking about the silent sculptors and how AI is teaching us their language. First, to understand how machine learning is changing the game, we need a quick primer on how glaciers transform the landscape. Glacial geomorphology, the study of these landforms, is a blend of geology, geography, and climatology, all trying to read the stories written in rock and ice. It all begins with snow. Over many years, layers of snow accumulate and compact under their own immense weight, eventually forming dense glacial ice. Once it gets heavy enough, gravity takes over, and this massive body of ice begins to flow downhill, like the slowest, most powerful river you can imagine. This movement is the engine of erosion, and it works primarily through two powerful mechanisms: abrasion and plucking. Abrasion is exactly what it sounds like. It's like a giant, continent-sized piece of sandpaper grinding across the land. Rocks, pebbles, and sediment get frozen into the base of the glacier, and as the ice moves, this rocky underside scours the bedrock below. This process leaves behind one of the classic calling cards of a glacier: long, parallel scratches in the rock, known as glacial striations. If you ever find these on a rock outcrop, you've found a compass pointing in the direction of ancient ice flow. The second mechanism, plucking, is a much more forceful process. As a glacier slides over bedrock, meltwater at its base seeps into cracks and fractures in the rock. Overnight, or during cold periods, this water refreezes. And as we know, when water freezes, it expands. This expansion acts like a wedge, popping and prying chunks of rock loose from the bedrock. The advancing glacier then simply plucks these fragments away, incorporating them into its icy mass and carrying them, sometimes for hundreds of miles. The combination of this constant grinding abrasion and forceful plucking, combined with the sheer weight of the ice, carves out a whole suite of distinctive landforms. When multiple glaciers erode a single mountain from several sides at once, they can sculpt a towering pyramid-shaped peak known as a horn. The Matterhorn in the Alps is the textbook example. Where two glaciers flow side by side in adjacent valleys, they sharpen the ridge between them into a knife edge called an arete. And perhaps most famously, the classic V-shaped valleys carved by rivers are gouged out and widened into broad, steep-sided U-shaped valleys, like the iconic Yosemite Valley. When the climate warms and these glaciers begin to melt and retreat, they don't just disappear. They leave behind all the rock and sediment they were carrying. This unsorted pile of debris is called till, and it forms ridges called moraines, which act like geological bathtub rings, marking the former extent of the ice. They also leave behind other strange features, like elongated, teardrop-shaped hills called drumlins, and long, sinuous ridges called eskers, which are the remnants of rivers that once flowed in tunnels beneath the ice. By studying all these clues, geomorphologists can piece together the history of past ice ages. But here's the problem. All these features tell us what happened in the past. Measuring the rate of erosion happening right now under active glaciers is incredibly difficult, dangerous, and expensive. This has left a huge gap in our knowledge. And this is where the story takes a fascinating, digital turn. In the last few decades, we've entered an age of unprecedented observation. A fleet of satellites, like Landsat, Sentinel, and Aster, are constantly monitoring Earth's glaciers. They provide a fire hose of data on their size, thickness, surface features, and most importantly, their velocity. The problem shifted from a lack of data to a deluge of it. How could scientists possibly process and analyze this flood of information effectively? Traditional manual analysis is slow, painstaking, and often subjective. The answer, as you've probably guessed, is artificial intelligence. Machine learning algorithms are designed to find patterns in vast, complex datasets, making them the perfect tool for the job. Initially, machine learning was put to work on relatively simple but crucial tasks, like just creating an inventory of all the world's glaciers. Algorithms like the U-Net architecture, a type of deep learning model, proved incredibly good at automatically outlining glacier boundaries in satellite images. This was a game changer, especially for mapping debris-covered glaciers. These glaciers are often so covered in a layer of rock and sediment that they look more like a rocky mountainside than a river of ice, making them incredibly hard to identify with older methods. From mapping, the next logical step was monitoring. By feeding AI algorithms a time series of satellite images, scientists can now automatically track changes in glacier size, volume, and flow speed. This gives us a near real-time view of how glaciers are responding to climate change. For example, AI has been used to monitor the formation of crevasses or giant cracks on the surface of the critical Thwaites Glacier in Antarctica. Tracking these fractures helps us understand the stresses within the ice and predict its future stability. But the most exciting frontier, the holy grail of this research, is using machine learning to predict the rate of glacial erosion itself. This is where it gets really clever. So what does it take to build one of these digital geologists? Well, an AI model is only as good as the data it's trained on, so the first step is gathering the right ingredients. The main data type is topographic. Digital elevation models, or DEMs, are high-resolution 3D maps of the Earth's surface, often created from satellite radar data. From these 3D models, scientists can extract all sorts of crucial information, like the slope of the land, its aspect, which is the direction the slope faces, and its curvature. All of these factors influence how ice flows and erodes. Next comes the wealth of satellite imagery. Optical images from satellites like Sentinel-2 are like photographs. They show us what the surface looks like, allowing the AI to distinguish between snow, clean ice, and rocky debris. Then there's radar imagery from satellites like Sentinel-1. Radar is amazing because it can see through clouds and works day or night. It's particularly good at measuring glacier velocity by tracking the movement of features on the ice surface between satellite passes. Finally, there's climate data. Things like air temperature and precipitation are fundamental drivers of glacier behavior, so they are a crucial input for any predictive model. Once all this data is gathered and prepped, it's fed into a machine learning algorithm. There are a few different types that have proven very effective. One popular choice is the random forest algorithm. You can think of it as an army of simple decision makers. It builds hundreds or thousands of decision trees and combines their outputs to make a final prediction. It's great at handling large datasets with lots of variables and can even tell scientists which factors are most important for the prediction. Another powerful tool is the convolutional neural network, or CNN. These are a type of deep learning model specifically designed for image analysis, inspired by the human visual cortex. They are brilliant at automatically identifying features in images, like spotting the difference between a glacial valley and a river valley just by looking at the 3D topography. This brings us to a groundbreaking study that shows the true power of this approach. Led by geographer Sophie Norris at the University of Victoria and published in the prestigious journal Nature Geoscience, the research team built a machine learning model to estimate the rate of future erosion for over 180,000 glaciers across the entire world. This was a monumental undertaking, They fed their model all the data we just discussed: topography, ice velocity, climate variables, and trained it to predict erosion rates. The model's predictions were stunning. It found that 99% of the world's glaciers are eroding the ground beneath them at a rate between 0.02 and 2.68 millimeters per year. For perspective, the high end of that range is about the thickness of a credit card. That might not sound like much, but over thousands of years, it's how you build a Yosemite. What was truly fascinating was that the model revealed the incredible complexity of the process. It wasn't just about how fast the ice was moving. The most important factors were a combination of temperature, the amount of meltwater at the base of the glacier acting as a lubricant, the type of bedrock being eroded, and even the amount of geothermal heat flowing up from inside the Earth. The AI found subtle patterns that were previously hidden. This study is a landmark because it provides the first comprehensive, data-driven estimates of glacial erosion for even the most remote and inaccessible regions on the planet. And its findings have huge implications, from managing landscapes and predicting how sediment and nutrients will flow into our oceans, to assessing the long-term safety of proposed geological repositories for nuclear waste. Now, despite this remarkable progress, using machine learning in glaciology isn't a perfect science yet. There are challenges. The biggest one is data availability and quality. Deep learning models are hungry for data. They need vast amounts of labeled information to learn from. For many of the world's glaciers, we simply don't have detailed on-the-ground measurements or ground truth data to validate the model's predictions. Another challenge is the black box problem. Sometimes, a complex neural network can produce an incredibly accurate prediction, but it can be difficult for scientists to understand exactly how it arrived at that conclusion. They can see the inputs and the output, but the internal logic can be opaque, which makes it hard to trust the physical basis for the model's predictions. But the future is incredibly bright. Remote sensing technology is constantly improving, with new satellites promising even higher resolution data to feed more sophisticated models. And scientists are developing new techniques to address the black box problem. One of the most promising is something called physics-informed neural networks. These are AI models that are designed to incorporate our fundamental understanding of physical laws, like the laws of thermodynamics and fluid dynamics that govern ice flow, directly into their structure. This makes their predictions more robust, more physically plausible, and easier to interpret. The ability to accurately predict glacial erosion has far-reaching consequences. For climate change research, it helps us understand how landscapes will evolve in a warming world. It helps us predict how the delivery of sediment from melting glaciers will impact rivers, dams, and coastal communities. For geological risk management, these models can be used to assess the stability of mountain slopes as glaciers retreat, and to predict the likelihood of catastrophic glacial lake outburst floods, a major hazard in places like the Himalayas and the Andes. So, in conclusion, the marriage of glacial geomorphology and machine learning represents a true paradigm shift. It's a powerful new way for us to understand the forces that shape our world. By combining the flood of data from our ever-watchful satellites with the pattern-recognizing genius of artificial intelligence, we are finally beginning to decipher the intricate language of the ice. The silent sculptors are starting to tell their secrets, and listening to them is absolutely vital as we navigate the challenges of our changing planet. Thanks for listening to G Fun Facts Online.